Okay, so today we will continue the last piece of propositional logic, and then we'll move on to the second part of this course, which is about associative programming, ASP, that you use as a keyword standing for this programming method. Okay, so we talk about three concepts. So first we define actually, before that we define valuation and interpretation. Okay. After that we define some notions that are derived from the valuation. So we talk about tautology, where the formula, the tautology is a formula that is true for all valuation. And satisfiability means that the formula is true for some valuation. Okay. Now, one question to think about is how are these two concepts related to each other? Okay. So how are tautology and satisfiability are related to each other? So this is a sentence saying that if you have a set of formulas f1 through fn, and you see that this is unsatisfiable. Okay, this is actually equivalent to saying that negation of f1 through fn, the conjunction of all these formulas, is a tautology. So on the one side, we talk about unsatisfiability, which is actually the opposite of satisfiability. Okay, and on the other side, we have a tautology. Okay. So unsatisfiable means it's a negation of satisfiability, meaning that there is no interpretation that satisfies all formulas. So for all interpretation, there is at least one formula that becomes false. So you cannot make all formulas to be true. Okay, that's what the left-hand side is saying. By the way, this if IFF means if and only if. It's a two-way implications. Okay. So when you say the set is unsatisfiable, meaning that for all interpretation, for every interpretation, there is at least one formula that becomes false. Okay? It's the same as when you put the whole formulas as a conjunction and put the negation, then this becomes always true. Okay? So if you're keen to the definition, you can figure it out why this makes sense. But before we do that, let's actually look at some example. So let me write this formula. So I wrote three formulas, P, Q, and not P or not Q. Is it satisfiable or not? Can you find an interpretation that satisfies all formulas? No, it's not possible because you have to, at least you have to satisfy P. That means P should be true and Q should be true. Okay? But if you have that interpretation, then you cannot satisfy the third formula. Not P or not Q cannot be satisfied. So this is unsatisfiable. This is an example of unsatisfiable set. Now what that means is if you put the negation and make a whole set as a conjunction of formulas, then this is a tautology. So this is unsatisfiable, and this is a tautology. So this is an example. If you have an unsatisfiable set, then you can form a tautology using the sets in that formula. And vice versa. If you have some formula of this form that starts with negation, followed by the conjunction of these formulas. Now if you know that this formula is a tautology, that means each of these components, P, Q, and not P or not Q, is unsatisfiable. Okay? And you can actually prove this. I'm not going to show the proof, but let me just illustrate this idea using the example, like here. Okay? So, when you prove if and only if statement, as you learn in natural deduction, you have to prove two things. One is assume the left-hand side and try to derive the right-hand side, and also vice versa. So let's try to see why it makes sense. When you assume, let's say this is unsatisfiable. So let's actually, we know that this set is unsatisfiable, meaning that there is at least one of them must be false for any interpretation that you apply. Meaning that if you negate that conjunction, that negation becomes true for any interpretation. Hence the proof. Okay? I just use the definition. Unsatisfiability means that there is at least one there is, for any form interpretation, there is at least one formula that is not satisfied. That means if you have an odd conjunction, this conjunction is always false. Which means that if you negate that conjunction, it becomes true for any interpretation. So that formula must be a tautology. And the other way is actually the same. So if this is a tautology, then not all of these conjunctive terms becomes true. So at least one of them is false, meaning that this is unsatisfiable. Okay? All right. So that's what you get. Okay, the proof is just to make this notation more formal, but the idea is actually the same. Yes?
What do you exactly mean when you say interpretation?
Interpretation is a function that maps signature to truth values. We learned that right after the function. Okay, so if you have PQR, okay, so that's the atoms. So the function that assigns truth values to these PQR, this is an interpretation.
So, okay. The 3 or 4 atoms can have innumerable number of interpretations.
2 to the power n.
It means the truth.
Okay. So if you are unsure about that, go back to the slide that we talked before. All right. So the next thing is obvious. So once you know this, of course, you can make a variation. So here, this is unsatisfiable if and only if this. It's actually the same statement that you can write here. If you flip this value, okay? So this set is unsatisfiable, meaning that the negation of this means it's actually satisfiable. And negation of this one is actually this is not a tautology. Okay? So these two statements are actually the same statement. I just write in a different form, but they actually mean the same thing. Okay? Question about this? So one thing that you can apply here is suppose you know that P if and only if Q. This is actually same as saying not P is equivalent to not Q, right? So these two formulas are equivalent if you apply the definition of equivalence. If you know that P is equivalent to Q, you can also find out that not P is equivalent to not Q. Okay? So in that sense, what I do here is this is my P, this is my Q. So I wrote in the first sentence P if and only if Q. In the second sentence, I wrote not P, roughly speaking, is equivalent to not Q. So these two statements actually convey the same meaning. Okay? All right. The next one is how the entailment and tautology are related. And somebody actually asked the question, and I also posted the response on the Piazza. So this is an answer. So when you say entailment, it means if you find any interpretation that satisfies these formulas, the interpretation must satisfy this formula as well. Meaning that if this is true, then this must be true for all interpretations. Okay? So if you don't know exactly what entailment means, you can actually rely on this proposition to understand the entailment in terms of the tautology. You just make all formulas in the premises as a conjunction, and if that implies the conclusion, okay, if that implication itself is a tautology, okay, then you can say the entailment is true. Okay? Slightly different way to say the same thing is, how do you know that G is not entailed from F1 to Fn? How do you know that this is not entailed? You can say that this is not, the right-hand side is not a tautology, meaning that there is one interpretation that satisfies F1 to Fn, but does not satisfy G. Okay? So let's look at example. So let's say if we have P or Q and not P or Q. Does it entail P? Does it entail P? No. If it does not entail, then what is an example? P is false. And Q is? Okay, so let's say P is false and Q is true. What happens to the formulas on the left-hand side? This is true, right? Because Q is true, so Q or whatever it is true. Okay, same for the next one, right? So when you apply this interpretation, by the way, this is an example of interpretation. P is false, Q is true. Okay, so if you apply this interpretation, these two formulas are true under this interpretation. But if you look at the right-hand side, this P is actually false under this interpretation. Okay, so the entailment does not hold. Meaning that P or Q and not P or Q implies P is not a tautology. And if you look at the thing, if it is not a tautology, it means that there is one interpretation that falsifies this formula, right? And what is that interpretation? Yeah, actually the same thing we can apply, right? We need only one interpretation that makes this formula to be false. So let's just use the same interpretation. Okay? So vice versa. If you know that the right-hand side formula is a tautology, then the entailment also holds. Or if your right-hand side is not a tautology, then the entailment does not hold. Okay? A very special case is when the premise is empty. So G is entailed from empty set of formula, meaning that G is a tautology. Okay? So some of the examples that you did in homework 1, okay? So we didn't have all the premises there, right? Many of them didn't have premises. And you can actually go back to these formulas and check each of these formulas is a tautology. Okay, you can draw the truth table and find out that those formulas that you proved in natural deduction are tautologies if the formula were derived from the empty set of premises. Okay? Question up to this part? Okay. The next one is entailment and satisfiability. Okay? Well, actually you already learned two things. Okay? And from this you can compose the third thing. Okay? So what we are doing is you learned what is tautology and satisfiability were related. And in the next slide, we just talk about entailment and tautology. Now we are trying to talk about this, which can be actually composed from the two known relationship. Okay, so if you do that, what you get is this. F1 through Fn entails G if and only if this set is unsatisfiable. Okay, so let's look at an example. Actually, we can use the same example. Actually, let's look at this one. Is this entailment true? P or Q and not P or Q, does it entail Q? How do we check the entailment? Enumerate all interpretations. There are 4 interpretations. Okay, and for each interpretation, check whether this interpretation satisfies these formulas. Then we also check whether the Q is true. Okay, so if you do that, you will see that actually this is true. This entailment holds for whatever interpretation that satisfies these two formulas must also satisfy Q. Okay, According to this relationship that I just said, this is unsatisfiable. Okay? Which means if you know that this one is true, right? This entailment is actually true, you can find that this set is unsatisfiable. Why? Well, because any interpretation that satisfies these two must satisfy this one, but if you put the negation, the interpretation cannot satisfy the negation. You get it? Let me repeat. So, by the definition of entailment, if you have every interpretation that satisfies these two guys, must satisfy this guy as well. Okay? Now, if you happen to choose the interpretation that satisfies both two, then entailment means that Q should be true, but now you have a set in the set not Q. So the interpretation cannot satisfy the third guy. So it's unsatisfiable. Okay? And vice versa, you can actually prove this same thing using the definitions. Okay? Any question up to this part? All right. Okay, so the next we talk about soundness and completeness theorem. So let's actually review this thing. So soundness means that basically, let me actually tell you about the history. So there are actually two ways to understand propositional logic. One is using only natural deduction. Another is using only the satisfaction and entailment and so on and so forth. Okay. So the first thing that we did was only using natural deduction. That was called proof theory. Okay, so it's only about the proof, how to write the proof for the sequence. The next, we learned interpretation, valuation, satisfaction, tautology, entailment, satisfiability. So those things belong to so-called model theory. Okay, so these are just two ways to define propositional logic. And what soundness and completeness theorem is saying is these two notions are actually these two notions coincide. So when you can understand in both ways, it does not actually matter. Okay? So soundness theorem means suppose you only know about the natural deduction. Okay? So you can prove the sequence. Okay? So gamma is a set of premises and you derive f from the gamma. And you're using the natural deduction rules that you did in the first part of the semester. If the sequence can be proved, okay, that's what the proof theory is about. Okay, the soundness theorem is saying that if you can prove the natural deduction in natural deduction, then gamma entails f in the sense of model theory. So soundness theorem is saying from the proof theory of propositional logic, you can go into the model theory of propositional logic. Okay? So if you can derive using these deduction rules or like calculus that you studied, if you can do that, then you can also draw the truth table and check whether the interpretation that satisfies all the formulas in the gamma also satisfies that. Okay? So that's what soundness theorem is about. If you can prove by natural deduction, you can also draw the truth table and check whether this entailment holds. Okay? The completeness theorem is opposite. The completeness theorem is if you can do everything in terms of the truth table by writing a big truth table to check the entailment, okay, which is probably a lot of homework problems that you're going to do this week is about drawing the truth table. If you can do that, there's also a way to prove that in natural deduction. Okay? So here I denote some informal description about this theorem. So soundness means that any formula that you derive from natural deduction is actually meaningful. It is actually sound. Okay? It actually conveys the real truth. Completeness theorem is opposite. Anything that makes sense as a truth can be derived from the calculus of natural deduction. Now, of course, this is an example that we talk about. You can prove these things. The natural deduction, we already did that in the, I think that was the midterm problem, right? Midterm or quiz? the quiz. So the last problem of the quiz 1 was about deriving this using natural deduction. But we also did it in class that the entailment is actually true. Okay? How many interpretations satisfy formulas on the left-hand side? Do you remember? There's only one. And that interpretation happens to satisfy T as well. Okay? So you can argue in terms of truth table. Okay, this is what you do with truth table, and this is what you do with natural deduction. If you can do in one way, you can do in the other way too. Now, why does it actually matter? Here's actually a question that we want to consider. Okay, so I give you this sequence, which is not P or Q implies P derives not P and Q. I'm asking you to check whether this is provable in natural deduction, and if so, show the proof. Anyone can do this? If you can show this convincing proof, I will give A plus immediately. So show the proof. Anyone wants to try? Come to the board, write the proof, and get A plus, and don't have to come to class anymore. Okay, I can just stop here, and I can wait until the end of the class. If there's somebody is doing, I can enjoy my drink. Anyone else? You can come to the board too. We can have multiple solutions. I said show the proof.
Oh, show the proof.
Yeah.
Can't show the proof.
Okay, then you don't get it. Okay. But so yes, he's actually right. There is actually no proof. Okay. Why is not provable? But how do we know that this is not provable? That's actually a more interesting question, right? Do you have a proof?
I was just saying, you can show it's not.
Yeah. Well, what do you mean by truth table here? Where is truth table? Yeah. So you start to use the theorem. Okay, so that's good. Okay, so exactly the reason that I bring you up here, the question is for that. So let me actually go from the beginning. So I ask you to determine whether there is a proof, and in fact there is actually no proof, so you cannot show the proof. But how do you know that there is no proof? So if you didn't learn entailment, if you didn't learn completeness or soundness theorem, okay, all you can do is try to derive the proof, derive this formula from the natural deduction. So remember, when you did homework 1, what did you do? You use these deduction rules in very complicated way. Sometimes it didn't actually work, but you had to try this and that, and until you find some answer, right? But however, if there was no answer from the beginning, if there is no proof from the beginning, how can that method be working? You will waste a lot of time. Right? No matter what you do, there is actually no proof. So you need to think in different ways, much different from what you were doing before. And that's where the soundness and completeness theorem is actually coming in. And for those who get the sense, can you tell me which theorem is actually used to say that this is not possible? Is it soundness one or the completeness one? Somebody says, is it soundness? Are you sure about that? Okay, so that's too much jumping, so let's actually go one by one. Okay, so let's try to see how to use these theorems. Okay, so when I said derive f from the gamma using natural deduction, so that's proof, right? So the method that we used was to show a derivation from f using the rules from gamma using the rules of natural deduction, and that's by definition. By definition, proof means that you show the sequence of derivation in natural deduction. That's by definition. But now, what you can do is this. Instead of showing the provability there, you can use this meta level of proof, which means that use the theorem, here actually the completeness theorem. The completeness theorem is saying that if you happen to prove that gamma entails f, then there is always a deduction of f from gamma. So now your test is reduced to prove the entailment. Okay? So what that means is the given problem was this. You have to show this. But if you happen to show this one, if suppose it was actually easier to prove the entailment than the proof in natural deduction, then this is actually a good way. So you show the entailment holds, okay? And then the completeness theorem is saying if the entailment is true, then provability is true. So combine these two ideas. So this is actually kind of modus ponens too. If you happen to, so this is completeness theorem is saying if gamma entails f, you can say that gamma derives f in natural deduction. So all you need to do is to supply the antecedent. So if you show this is actually true, then using this one and this one, you can derive the consequent. That's modus ponens or implication and elimination rule in natural deduction, right? I'm actually using natural deduction in two different levels, so let me not confuse you. So one thing is you show that gamma entails f. Then by the completeness theorem, you can say that gamma derives f.
Is it not possible to use natural deduction to show whether or not something is provable?
If it is provable, yes, you can show. But if it's not provable, how can you show?
Without using entailment, can you prove that something is?
How can you do it? How can you do it?
That's my question.
I don't know either. Okay. Maybe there is another level of meta-level theorem that we can use, but this is what people do. Okay, are we clear here? So in order to prove that something is derivable, you can do two things. You can just show the proof directly, or you can use you can prove the entailment, and then using the completeness theorem, derive the probability. Okay? Good. Now, the next question is about what you were saying. How do we show that this is not provable? How gamma derives f is not provable. Okay? So the hint is actually the soundness theorem is helping here. The soundness theorem is saying that if sequence is provable in natural deduction, then gamma entails f. Okay, there's a slight problem here, slight problem. Our test is to show that this is not provable. On the other hand, soundness theorem itself does not mention about it. It actually talks about provability, but not the improvability. So how can we do that?
Take the contrapositive.
So here, yes. Right. So what is the contrapositive? Contrapositive means, so let's say we have statement like P implies Q. This is conditional statement, right? If P, then Q. Okay, let me actually write in English. If P, then Q. This is called conditional statement. Contrapositive means if not Q, then not P. And these two statements are actually equivalent. P implies Q is equal to not Q implies not P. So instead of using the first form, we can use the second form. So that's called that's a contrapositive of soundness theorem, meaning that if gamma does not entail F, then so I use two not both in the antecedent and the consequent. If you can somehow check that gamma does not entail F, then you can say that there is no proof in natural deduction. Okay? So let's go back to this problem. So I was asking about I asked this question, right? Is it provable or not? In fact, there is actually strong evidence that this is not provable. If you try to prove this million of days, you probably still cannot find it, and then you start to think maybe we have to approach in different ways. So how do we prove that this is not provable? Now let's use the contrapositive of the soundness theorem. If you can somehow show that this formula does not entail this, okay? Then you can say not P, okay, is not provable, right? That's what the contrapositive of the soundness theorem is saying, okay? So you have to derive this thing, okay? You want to prove, you want to say that there is no proof of this deduction. Then now the goal is to prove this. Once you prove this, we can derive this, right? So how do you prove this? This is actually much easier, right? How do you know that this entailment does not hold? For the entailment not to hold, how many interpretations do we need? Just one, yes. So what is that interpretation? P is true, Q is true. Okay, so let's use that. So suppose P is true, Q is true. What happens to the this formula? What is the evaluation of this formula under the interpretation that P is true, Q is true? Is true. Why? Because Q implies P is actually true. True implies true is true. So true or anything is actually true. So this becomes true. What about this? This is false because P is true, so now P is false. False and true is false. So left hand side is true, right hand side is false, so entailment does not hold. Since we know that entailment does not hold, by the contrapositive of soundness theorem, we say that the sequence is not provable. Done. Okay? Right. So, okay. So in other words, these two statements are the same thing, right? So soundness and completeness theorem is saying this can be derived if and only if this. But this is also same as saying that if it's not derivable, then entailment also does not hold, and vice versa. So sometimes you want to use the positive version of this theorem. Sometimes you want to use the negative version of this theorem. Okay? It depends on how you do it. Okay? Are we clear about it? Okay? Right. Alright, so the next thing is about CNF and DNF. So CNF stands for conjunctive normal form, and DNF stands for disjunctive normal form. So in the theoretical computer science, there's something called normal form, where the syntactic object could be very complex, but they somehow reduce to very simple form. Okay, so any complex propositional formula can be turned into CNF form or the DNF form. Okay, so that's what we'll do. So first, what is actually the conjunctive normal form? And this is a bit tricky, so we are going to do some quiz. So let's look at the definition carefully. Okay? So, first, the definition. We know what is an atom, right? So atom is P, Q, R. What is a literal? Literal is either an atom or its negation. Okay? And then we talk about simple disjunction. And simple disjunction is just disjunction over these literals. Okay? Now, what is a conjunctive normal form? Conjunctive normal form is this form. It's called conjunctive normal form because it is a conjunction of many formulas, F1 through Fn. But now if you look at each of these formula, Fi, they are simple disjunction. Okay? So it's basically conjunction over disjunction of literals. That's what conjunctive normal form is about. Okay, are we ready to do this challenge? Okay. So I'm going to give you, let's say, true, false. Let's do that. It's always fun to do. So, let's look at this. Okay, so is this formula conjunctive normal form? So this is again that you have to use the pattern match. Okay? So find out where is the F1, Fm, okay, and what is actually L1 and Ln in each of these conjunctive term. Okay? Okay, so let's check that. Okay, so some people are still doing. Alright, so 2/3 was saying true, 1/3 is false. The answer is actually true. Okay, so let's see why. So this is again a pattern match. This part you can read as F1. This is F2. This is F3. So there are three simple disjunction here. Okay, so F1 is a simple disjunction because that's a disjunction over literals. Okay, each of them is not Q, P, R, they are literals. Same for the F2. Now P is a literal, R is a literal, disjunction over them is a simple disjunction. Now Q is a bit tricky, but if you look at the index carefully, you don't actually need a disjunction. If you have only one, that's also called simple disjunction by definition. If you look at the second bullet, a simple disjunction has this form. When n equals 1, there is no disjunction. There is only one literal L1. And that's what the third case is about.
Can we think of this as either product of sums or sum of products?
Something like that, yes. But don't go into that yet because you may get confused soon. Okay?
If we talk about only F1 or only F2, then those are CNFs by themselves too.
Only F1?
Yeah.
Okay, we'll talk about that later. Okay? So, the next one, okay, let me actually erase these. Oh. Okay, so second formula. Look at the second formula. Okay, and let me finish off this and true false again. Let's start. So second formula, is this CNF or not? Okay. Are we done? Okay, it is false. Yes, it is false. Why? Because if you try to match this one, the first one, this one must be of simple disjunction, meaning that disjunction over either atom or negation. But this one has negation over more complex formulas. So this is not CNF. Now if you take this one, this is actually related to the question that was raised earlier. If you take this one, is this CNF or not? It is also CNF. And in this case, M here equals 1. There's no conjunction, but it is still called conjunctive normal form because this case, M equals 1 happens to be this. Okay, so when M equals 1, it's only F1, which is a simple disjunction, and this is simple disjunction. Okay, good. Is this CNF? Is this? Anyone?
No.
This is not a CNF. Why?
So it's not allowed.
Yeah, but why is it allowed? Why?
It's not.
Yes. So when you go into the base case, you have to have a literal, right? Literal is an atom or the negation of atom. Top is a zero place connective, so it's not a CNF. Okay, very good. Disjunctive normal form is defined in an opposite manner. So just turn the conjunction into disjunction, disjunction into conjunction, then you get disjunctive normal form. Meaning that when you say simple conjunction, this is a conjunction over simple things, which is a literal. Now, disjunctive normal form has the disjunction over simple conjunction. Okay? So, is this DNF? In this case, what is M and what is N? Okay, let's say what is M here? M is 3, yes? So here, each of them counts for these formulas. So this is F1, F2, F3. Now each Fi happens to be also a simple conjunction where N equals 1. Okay, so this is DNF. What about this? Is this DNF? What is M in this case? M equals 1. What is N in that first Fi, F1? 2, correct. Good. So, I mean, this is just a definition that you can try. So, obviously the quiz that I can give you is true or false. Okay, so is this DNF or CNF? And I said typically that the students understand halfway can get more than 50%. So, okay, try to understand in a complete manner. Okay. All right. So, what is the theorem on CNF and DNF? So basically, any propositional formula can be converted into CNF or DNF. There's some condition that we have to say. So the signature should be non-empty. I will talk about, maybe if you have time, we'll talk about why this condition is needed. But basically, the theorem is saying any formula can be turned into CNF or DNF in an equivalent way. So let's actually play with that. So we know that this top is not a CNF. It's also not a DNF. Okay. Can we turn this into CNF or DNF?
Yes.
So, what can be that formula? So let's try to turn into CNF first. What is the formula to do that?
P or not P.
P or not P? Okay, so first, you think that this is a CNF. There are actually multiple claims to check. first we have to check whether this is CNF, and also we have to check whether this formula is equivalent to top. Right? Actually, the second is easier to check, right? So P or not P is always true, no matter what value that you assign to P. So, and top is always true, okay, by definition. That's good. So these two formulas are equivalent. Now we have to check whether P or not P is CNF. So what is M in that case? So M here is F1 conjunction with F2, Fm. This whole thing is one conjunctive term. There is actually no conjunction symbol here, but this is one conjunctive term there. So M equals 1 in this case, yes. And in that case, we have to also look into this formula, where P or not P is a simple disjunction, and it is the case. So this is CNF. Good. Are we together? Probably not. Okay, some of you may have lost somewhere. Okay, so after this lecture, maybe you want to come back to the definition. Okay? Yes.
So we say M equals 1 because, like in our formula for CNF,
Mhm.
P or not P is equivalent to like your F1.
Yes. Right. When M equals 1, so let's actually go back. So when M equals 1 here, this is actually same as just of F1. And just F1 should be a simple disjunction. So P or not P is a simple disjunction that is in F1 here. Okay, good. All right, now we have to find DNF. What is the DNF form of this top? We can use actually the same formula. In this case, what is M? M is 2. So this is actually the same formula, but it is a disjunction over two formulas. And each disjunctive term is also a simple conjunction. Okay? So, depending on how you view this, the same formula can be viewed as CNF or it can be DNF. Good. Similar thing happens here. So, bottom. You can do P and not P. This can never be true, right? Is this CNF? Well, if it is CNF, what is the M here? What is M here? 2. It can be also DNF. Okay, what is M here? 1, correct. Good. So you guys know that. You can actually convert more complex formula like this into CNF and DNF. Okay, and the equivalent transformation that I gave you as a homework problem can be useful here. So let's actually try to do that. So when you have this, obviously this is not CNF or DNF, right? One thing that you can do is to use De Morgan's law. And if you do that, okay, you will get not P, and conjunction inside turns into, disjunction inside turns into conjunction. And not Q and I. We can do one more time. We can do not Q or not I. Okay? Now at this point, I can actually stop and claim that this is one of the CNF or DNF. Is it CNF or DNF? The last formula that I wrote, is this CNF or DNF? Is this CNF? It's a conjunction over simple disjunction, so that's CNF. But is it DNF? It's not. Okay? So in order to turn into DNF, I can further distribute conjunction over disjunction, another homework problem that you have to prove. Okay? So when you do that, you will get this one. This is pretty much like algebra when you have a multiplication distributed over addition. Okay? And now after you do this, the last formula is DNF. It's a disjunction over simple conjunctions. Okay? So this is CNF and this is DNF. Okay? All right. Okay. So now our textbook actually has a general procedure to convert into CNF, but maybe I'll skip this for now, and I'll move on to the next subject. Okay. All right. When you go to a class like 340, you will learn recursive descent parser, and basically the idea is same as there. So I can skip this for now. All right, so we are done with the propositional logic, and as I promised, the next is to use this as a programming language. And in particular, we will tweak the propositional logic a bit, so that will take us a few classes, and then we'll get into the actual programming. So the idea is this. When you're trying to solve problems using computer, what do we do? So we first need to understand what is the problem, and then you convert into the form that computers can understand, and the computer generates output, and from this you interpret the solutions coming out of this output. Okay? That's how you do. Now, in terms of the typical programming or procedural programming that we do, how do we make the computers understand the problem? You have to do programming. Okay, so programming is a conversion from problem to some program. And then you execute the program, and that will generate some output. And you interpret the output, that becomes the solution to the problem. Now, in the declarative programming that we are going to study now, is slightly different. When you try to solve a problem, you're going to model the problem into certain representation, but you don't necessarily give an algorithm. Okay? And you just ask computer to solve based on the specification, and then the computer returns the output, and you get the solution. Okay? So one of the methods in the declarative programming is called answer set programming. And this is actually very has a very rich history and a lot of things done. But for this class, we will just look at some initial basic of this programming method. Okay. So we are going to use it for some computer science related subject that we are going to learn. Okay. So this is a declarative programming paradigm. Declarative here means that you don't necessarily tell the computer what to do or how to solve this problem. You don't do that. But you just describe what is the problem. Okay, you represent the problem, and the rest of this thing should be done by the programming platform automatically. Okay, so its theoretical basis is called answer set semantics, or also known as stable model semantics, which is slightly tweaked from the propositional logic. Okay, so we are going to learn that. It has very rich language construct. Default, recursive definitions, aggregates, and preference, which we are going to learn later. So for now, the programming that we are going to do here is you start with the problem, and then the modeling here is to write an answer set programs. So you are going to write some answer set program, and the execution here means solving this program using some special engine called ASP solver, answer set programming solver. Okay. So the basic idea of this programming is you represent the problem by a set of rules, and then find answer sets using ASP solver, and then extract solutions from this. So this is N-Quin's puzzle. So maybe let's actually illustrate the idea here. So this is a typical problem, benchmark problem in AI. So you have some n-by-n chessboard. Okay, let me write the color. Okay. So let's say we have 3x3 chessboard, and we have to play 3 queens in this grid, but no 2 queens can be on the same row or column or diagonal. Okay, how many solutions are there? many solutions are there? I mean, it's like a tic-tac-toe, right? You have to place 3 queens, but no 2 queens should attack each other. Attacking here means same row or column or same diagonal, right? How many solutions are there? There's no solution. Okay, good. What about the 4 by 4? How many solutions will be there? Well, let's do this. So let's say 1, 2, 3, 4, 1, 2, 3, 4. Okay. So give me the row number first, and then column. 1, 1. Okay. 2, 2? No, 2, 2 cannot be, because if you put 2, 2, then it attacks. So 3, 2. 3, 2 here. Okay.
2, 4.
2, 4. Okay. Huh? 4, 4, no, no. That doesn't work. You have to place 4 queens now because it's 4 by 4. Where do you put the 4th? Huh? So no solution? Haven't you played this game before? If you're doing AI, you will play this kind of game a lot. Okay? How many solutions will be there? It's 4 by 4, right? 0. It's actually 0 is not the correct solution. It happens to be this way that I know immediately somebody says some position, I know that there cannot be a solution because of the bad choice. But if we avoided that choice, we could have gotten a solution. So let's actually try different one. Somebody says 2. Okay, anyone say that what is the position to fill? 1, 3. Okay. And 2. Let's look at the row 2. Where to put? 2, 1. Okay. In 4, 2. Wait.
3, 4.
Okay. So that's one solution. Another solution is to take this 90 degree from. Okay, so that's another solution. Good. So the problem here is, suppose you have any size of grid. So let's say you have n by n. Here is actually 8 by 8 grid, and there are actually 92 solutions in this case. How do we use programming to generate all solutions? If you learn this language, then this is actually the whole code. Okay, so the first line is actually very simple. You don't have to know this now because I didn't teach you at all. But there are actually 3 lines of the code. This %sign sentence is just a comment. Okay, so the actual line that corresponds to the programming is 1, 2, 3. So you can write 3 lines of code to solve this n-queens problem. The reason that this becomes succinct is because you don't have to say how to solve this problem. You just say what is the problem itself. If you read the comment for now, that's actually how the rule is. What is the rule specifying? So the first rule, the very first line is just the type. So there's a number that goes from 1 to n. This line is saying that each column has exactly 1 queen, which is obviously one of the requirements for the n-queens problem. 2 queens cannot be on the same row, and 2 queens cannot stay on the same diagonal. So this is actually just the problem specification in English, and all you need to do is turn this into some logic form, and then the computer will find the solution for you. And in fact, if you run the code this is Klingo is the engine that we are going to use among the many other ancestor solvers. If you type this in the command line, okay, this is the file name, and this is the parameter n is now 8, so it's 8 by 8 grid, then it will find the solutions. In fact, you can find all solutions if you put 0 at the end, then it will generate all 92 solutions. And timing is actually very efficient. It's just 0.009 to enumerate all 92 possibilities. So you will learn very powerful programming method. We don't have to know how to design the data structure here or the algorithm, but as long as you specify the problem correctly, then using logic, or the engines that understand the logic, they will find the solutions. Okay, so that's the subject of the next class. Okay, so let me stop here, and I'll ask the TA to come here and explain to you about the grading criteria for the test, and we'll distribute.